today we have a seminar by Chris Branson, a professor from Ireland currently, right? He's visiting with EDU program on our faculty for this week. So if you get interested in the topics that Chris will present to you, there's still some time to just get in touch and have like a quick networking chat. So I invite you to do this. And again, thank you for coming, and the floor is yours, Chris.
Thank you very much, Maria. Okay, so what I'm going to talk about today is something called model averaging, and particularly Bayesian model averaging. And the idea is that there's a lot of models that you can use for spatial data. And of course, one of the problems that you always get is you've got your data, but you don't know in reality what the correct model is. You fit a model and you hope it's correct, and there are various ways of trying to test whether particular models are correct. Certainly in ordinary sort of classical statistical inference, things like hypothesis tests are really there to do that kind of a job. But there's another way of thinking about this, which is, if you like, when you've got actual data, the model that you don't know for certain that the model you're applying to that data is the correct one. And really, you know, there's possibly theoretical reasons why there might be more than one model. And how do you deal with this? And a fairly traditional approach is to sort of try to decide which one's the best. But this is a slightly different way of thinking about it, where you acknowledge that some of the models you hypothesize might encapsulate the situation quite well, but they might not be perfect. And this is particularly true, I think, when you're dealing with social and economic data. If you're dealing with some other kinds of data, possibly say from chemistry or a topic like that, you can derive a mathematical relationship between the variables you're measuring, and possibly you're comfortable with that idea just down to a number of few unknown coefficients. But when you're dealing with a lot of social and economic data, that's probably not true. You suggest models because you make certain assumptions in the theories, but the reality might not be exactly that. And even if your model is quite near to perfect, there can be other issues in terms of actually trying to measure the variables. The things that you want to measure, or the things that you think you're measuring, might not actually be what's happening. So, for example, if you're looking at incidence of disease, then sometimes people don't report or don't even realise they've got a particular disease. So things will be undercounted. If you're looking at that geographically, then there's a further complication in that things to do with non-reporting, for example, may be different in some places than in others. So that's kind of the sort of issue we're dealing with here when we have a situation like that, where we've got a number of quite plausible models and we don't know which one's best. And as I show here, the title sort of suggests that what we then do is some form of averaging the models based on various information in the data, and that's what I'd like to talk about today. I'll just get my notes up there, sorry. Hang on, one moment. Yep. Yeah, so we'll start off by, again, sort of thinking a bit about, whoops. Wait a sec. Oops, sorry, in an attempt to try to get that. Yeah, sorry. As a starting point then, when we have multiple models, as I said, a traditional starting point is just to say, well, which of these models is true? So you're given a number of competing models, and you want to decide which one is actually the correct one. And something like, if you've used, for example, AKA information criteria to select models, then that's the idea. You basically choose the one that's got the best AIC, and you say, okay, well, that's the model we're going to use. And kind of what we're doing here is essentially a sort of soft version of the above, where we say, rather than saying, which one's got the best score, you can, for example, say, well, given one of my list of models is true, what's the probability that each individual one is true? And if, for example, you get sort of, say, from 2 or 3 models, if you have, say, 3 models, but one of them has a probability of being true given the data of 0.98, and then the others are just 0.01 each, then it's pretty clear you should go with the first model, the one that's got a probability of being true of 0.98. But maybe you get something like, 0.6 and 0.4 for 2 models, something of that sort. And if that happens, then there's not such a clear case for just taking one of the models and ignoring the other one, and therefore you get what I might call a soft version of the inference there. So whereas AIC tends to just point you at a particular model to choose as the best one, what this is saying is there's a number of quite good ones, and it could be one of those. So that's in terms of inference. What we also want to think of a bit is in terms of prediction. And in one sense, this is the way that AIC works. It's basically trying to find which model is the best predictor. But actually, on occasion, rather than just picking a single model out, again, you might want to actually combine the model predictions for a number of different models, and again, get a weighted average of those based on the probability of which of those models is likely to be the correct one. And then, by sort of combining these action predictive distributions, they're not just the predictions, but the actual probabilities associated with each prediction, you then get a mixture distribution, which you can use as your prediction distribution. So instead of just saying, okay, so if we start off with just model 1 has sort of this prediction, x1, model 1 has that prediction, model 2 has sort of x2, and just we'll keep it simple, the probabilities of them having seen the data is p1 and p2, then we would actually have obviously just a model p1 x1 plus p2 x2, and you could do that for lots of different models. But what we're also saying is, supposing this is predicting something, we could actually have a probability density function f1 x1, and this would be f2 of x2, then, f1 of x and f2 of x, where x is the number we're trying to predict, then we could actually just have p1 f x plus p2 f x. So basically what we're doing there is coming up with a probability distribution from the two possibilities of the two models being true. So that's the kind of idea, that's a sort of starting point. And in particular, what we're going to think about most today is probably this part of the starting point. So particularly trying to work out which model is true, and then how do we combine the posterior distributions. So here's a sort of motivating example. Basically what we've got here is, supposing you're waiting for a taxi and it's already late. What you're concerned about is that you're going to miss a train, and you want to estimate how long you're likely to need to wait before the taxi arrives. Now, there's a lot of reasons why the taxi might be late. And, one of them, maybe the taxi's stuck in traffic. 2, the traffic was held up because the previous customer needed help unloading shopping or something. So, the taxi was going to go to one place, then come to you, but it's taking longer than they thought at that intermediate place, and that's caused a delay. There was an administrative error, so when you book the taxi driver got given the wrong time, so therefore isn't coming now. Maybe the taxi driver is not very good and has got lost somewhere, so they haven't found where they're supposed to be. Perhaps the most worrying one, maybe the taxi was involved in a road accident. Now, in one sense, what we've got here is what you call equifinality. So we've made an observation, i.e. that the taxi hasn't arrived yet, but there's lots and lots of possible processes that could lead to that happening. The outcome of all of those, at least up to this point, is that the taxi is at least 5 minutes late or whatever. So any of those could have caused that to happen. But what we sort of have on top of that is what you might call, instead of just straightforward equifinality, we've got weighted equifinality, because some of those things are more likely to happen than others. So it's probably more likely that certain things are the reason than other things. And that's sort of the idea here. And the idea then with Bayesian model averaging is that the thing you're interested in here, the number you're interested in, would be the delay time. Okay, perhaps it's a bit heartless to say you don't care whether the taxi's been in an accident, but in terms of just the practical problem of trying to get to the station in time to catch your train, then your main concern is the delay time, regardless of what's caused it. These scenarios could perhaps be modelled, and each of them would of course have different parameters. So let's say, because I've come up with 5 things there, that I've got models M1 to M5. And as I say, possibly because you've already looked at some data about taxi delays, which are represented by D here, then you could have probabilities that each of the possible scenarios could have happened. So probability of model 1 happening, given your previous data, up to, in this case, model 5. Now, what you can also do is model the delay times individually for each of those scenarios. So obviously some of them might give you a longer delay than others. And if you sort of looked at the delays with previous data about how long taxis have been delayed due to each of those possible reasons, then you've got basically the different parameters, but giving you a probability distribution on the delay time given a particular model and given the known delay time. Now, really what we're doing here to get the model averaging for this is we're interested in the waiting time, and we have this previous data about taxi delays. So all we're doing is something quite straightforward. We're basically combining the 5 distributions by saying that the probability of the waiting time given the delay, well, there's 5 possible models, so we basically work out the probability for the delay time given each of the models 1 to 5 and the data, and then we multiply that by the probability that each of the models is the correct one. And when we do that, we then end up with basically sort of margined out which model it is. So now we've got a model just saying how long is the waiting time going to be, given the information we've got in the past. So what we've kind of done is we've sort of saying, well, we're only really interested in what the delay time's going to be, not what the cause was. So we're trying to sort of average out over that, but it has to be a weighted average because each of them are a little bit different to the likely to happen. Now, that's an example that's not really spatial. I was just describing a process of taxis getting delayed, and well, it's sort of spatial because the taxis are going on roads and things, but it's not really spatial data. We're just interested in delay times. But this idea of looking at different models and trying to see which of them is the most likely to be the case, and also what on average is the overall distribution if we have different probabilities for each of the models, certainly can be usefully applied to spatial modelling. So I could, for example, come up with a spatial regression model using different spatial varying coefficients. So something a bit like geographically weighted regression or some other model of that sort, where basically what we've got is regression of some variable y is equal to sort of beta naught x, u and v, plus beta 1 u and v x1 plus and so forth, plus an error term. Now, okay, so that's a spatially varying coefficient regression model where UV here equal location. So it's a regression model where there's a linear relationship between the predictors x1, x2 and so forth and an intercept term. But these values actually change with location in space. And that's the sort of model like geographically weighted regression. There's other ways you can specify it, but the idea is that the coefficients in here vary across space, and these other things, x1, x2, are predictor variables. So, for example, you might be looking at the added value to a house if it's got a garage, and that would just be a 0.1 variable, but in some places it would add more to the value of the house than in other places. And if you have that, well, you could actually have a model where some of the variables were spatially varying and other ones weren't. So you could have another alternative model. That might be M1. M2 might be that the intercept term, for example, varied with space, but the coefficient for x1 was just fixed everywhere. And if there were several predictor variables, then there's actually a lot of possibilities there. You know, you could have each one of them either having a fixed or a varying coefficient. And to start off with, you don't actually know which of these models is the correct one. And by using something like Bayesian model averaging, you could then work out the probabilities of each of them being correct, and then combine predictions to allow for this. So, you know, if there's some uncertainty as to whether, for example, this coefficient here, beta 1, varied across space or it didn't, then you could actually find, you know, probability 1 for this model, probability 2 for that model, and combine the predictions weighted by those two probabilities. Also, because essentially these coefficients have the same meaning, although in one case one of them is fixed over space and the other one it varies, as in they have sort of the same meaningful dimensions. So, for example, if it was the value added by having a garage, then that might be an amount in euros or zlotys or whatever. So the two things mean the same thing in the two models, you know, how much change in price you get for adding a garage. Then you could reasonably actually use the model averaging to get an estimate of the coefficients there. And what it would do is if there was some chance of it being spatially varying, but also some chance of it being fixed, what you end up with is sort of something that's like kind of P1 times beta 1 U V, and let's call that beta 1 1 for model 1, plus P2 just beta 2 prime, but where that one's just the estimate of beta when it's a fixed thing. And so what it's done there is it's kind of given you usually something that has a bit less spatial variance, because, you know, one of those things is a constant, the other one isn't. But the idea is you can combine the two models to get a combined model letting these two things out. And as I say, I've done that there with just two cases, but if there were, say, 4 variables in there, then there's essentially 16 different possible models in there. By making each of the coefficients either fixed or varied, you could get 16 probabilities, and then you can sort of see which of those models are the most likely ones, and again you could combine those using that sort of model. So that's one example. Another example is if you're using something like some sort of model with, like, conditionally autoregressive model for the error term. You might have that defined on a contiguity matrix, but you're not sure which contiguity matrix to use. So you can actually calibrate the model with different contiguity matrices, get the probabilities of each of the models being true, and then combine your models using that. So again, it's this idea of, rather than necessarily just going for the one with the highest probability and ignoring the rest, you actually make use of the information from all of them. And as I say, that's particularly useful if there isn't much difference between the sort of best performing model and the model that performs least well. And then there's a final example I've given here, which is to look at the situation where I'm trying to model count-based regressions, so counts of things, and the response variable could have a Poisson distribution, could have a zero inflated Poisson distribution where not all of the cases get reported, so you get more zeros than you would expect in the normal. Similarly, you could have a negative binomial distribution, which is also a count distribution but more clustered, and on top of that, a zero inflated negative binomial distribution. So these aren't just having different models for the parameters in the model, these are actually just entirely different distributions. But again, the point is, you can come up with ways of estimating which of the models is most likely to be true given your data, and then basically draw inferences on the assumption that they each have varying probabilities of being true. So it's useful for a lot of spatial geographical problems. And just a few further observations about this is to note that basically these sort of estimates, or actually posterior distributions from a Bayesian model, can be used for any parameter that's common to all of the models. So, for example, though a Poisson distribution and a negative binomial distribution are just entirely differently specified, if you say that you've got a zero inflated Poisson and a zero inflated negative binomial, one of the parameters is the probability of the number not being reported and that counting as a zero. And that's in both the zero inflated Poisson and the zero inflated negative binomial. So if you weren't sure whether your data had either of those two distributions, you could actually still get a model averaged estimate of the probability of non-reporting, because that was a parameter that had the same meaning in both of the models. Some of the other aspects of the model were different, but not that part of it. So that's an important point. And it can, as I say, also be things like particular regression coefficients included in a number of competing models. And the other thing, unlike, say, likelihood ratio tests that you get in sort of classical statistics, the models don't have to be nested. The usual idea with a likelihood ratio test is that one model is sort of a more specific version of another one. So, you're testing whether some of the regression coefficients are zero in one variant of the model, whereas in the other, any of them could be non-zero. So one's a sort of subset of the other. That doesn't apply here. So, for example, you could compare a Poisson and a negative binomial model where they're not even the same distribution using this sort of approach. And as I've said already, one of the key things there is when several models all perform well, this approach makes use of the information from all of them rather than just discarding anything except the top performing model. That's one of its examples there. So, for example, doing the approach I've just been advocating for regression, if you compare that to something like stepwise regression as an approach, then stepwise regression does, basically come up with a means of selecting a single regression model out of a number of possibilities. This, kind of averages over them instead. But the one little warning that comes with it is that does only make real-world sense if the parameter that you're estimating over several models does have the same interpretation across the models. So, as I say, it makes sense, for example, to look at the probability of non-reporting for both Poisson and binomial distributions, because that thing means the same thing, but possibly some of the other parameters don't mean the same thing. So, if you look at the way the negative binomial distribution is specified, or some specifications of it, the other two parameters in that aren't the same as the mean in the Poisson distribution. So you have to be a bit careful with that and assume that, when you are trying to estimate parameters across two models, that the parameter you're estimating is essentially the same thing. And that actually does still work over quite a lot of possibilities. So, for example, one model where the parameter is zero and the other where it's allowed to be any value, then you can still combine them. It's just that means you've got a certain probability of it being zero against whatever probability you're getting from the other model. But it does have to have the exact same meaning. So that's a bit of the the theory underlying all of this, or some of the ideas, well, perhaps of the theory. But I'll now try and give you a couple of examples. And one of these is to do with the Irish COVID-19 data. So when the pandemic hit Ireland, we obviously have some data about this. One of my jobs was actually to help do the modelling of COVID-19 in Ireland. So this is sort of comes a bit from personal experience. And the particular thing I'm interested in here is, for this study, is what happened in the very early days. And there are complications in that. So for a start, the numbers would have been relatively small. You know, I'm talking about maybe the first 2 or 3 weeks. And I think one of the lessons that was kind of learned from this was just the fact that, well, when you actually look at the early days of some sort of pandemic like this, of course, one of the issues was that not everybody even knew what the virus was, you know, that didn't understand what its characteristics were and things like that. And what, you know, we're trying to do, of course, is to model and to monitor the relative levels of COVID-19 in different parts of the country. But there are all kinds of difficulties with this. A lot of cases didn't get reported. Now, okay, this, you know, what I'm not trying to do is sort of point the finger at people who didn't report that they had COVID, because there's all kinds of reasons why the cases didn't get counted. In the very early days, some people didn't actually know that they had it, you know, that they got the symptoms, but they didn't know they were actually the symptoms of COVID-19. You know, what people were advised to do at that point was to go to a testing centre and get tested. The other complication is that the testing centres themselves varied in accessibility throughout the country. So in some places it was a lot easier to get to a testing centre than others. Again, don't forget this is the early days, so people are actually working out the best ways to actually set up the centres and where to put them and so forth. So, you know, a number of cases didn't get reported for that reason. Another reason is that, of course, in some cases, COVID-19 was asymptomatic. So you could be infected and carrying the virus, but you'd be lucky enough not to actually exhibit a lot of the symptoms of it. And so you'd be walking around thinking you'd not got COVID when you had. And that, of course, leads to quite a few problems, because you could infect someone else and then they did get the symptoms, but they had no real idea as to how come they got that. And unless you have some degree of compulsory testing, you're not really going to know about the people that had it that way. So basically there was always a bit of an undercount. And particularly what we were concerned about was the undercounts in the early days. So I think we started, for example, I've taken a particular date here, the 22nd of March, and I'm looking at, for each county, the number of reported cases that occurred. And the other reason, of course, is that for not reporting, is that when the samples go to the testing centre, it takes a little while for the tests to actually be carried out. So the numbers of the days reported aren't actually the day. There's usually a bit of a lag. And at times, if there was complications actually with the operation of the testing centres, you got more of a lag, and that was some reason why some days also some cases weren't counted. So as a starting point, I can model these using a zero inflated Poisson distribution. So we've basically got this probability here, theta, which is the probability of a case not being reported and giving a count of 0. And then the other possibility is that cases do get reported, in which case we've got a standard Poisson distribution. So we've got a probability of theta of getting 0, or a probability of a count of n, which is 1 minus theta times the ordinary Poisson distribution equation there, formula there. So when you get zeros, you get both kinds of zeros there. You can get a 0 because it's actually a Poisson distribution, we just happen to have a value of 0, or it might be due to non-reporting, but then that's actually counted. So if you work out the probability of 0 in there, it's that theta, i.e. the non-reporting possibility, and then 1 minus theta times, in there, the probability of n being equal to 0. So you get, which would be, it would be e to the minus lambda. So it's basically theta plus 1 minus theta times e to the minus lambda, and then for any of the other counts, it will be something more than, it'll be something less than the standard Poisson amount, because of the inflated number of zeros in there. So that's a sort of model that we've got. This is my data. So this is my counts of cases for Dublin on that particular day. And the key thing there is the highest number was in Dublin there, and also it was relatively high in Cork. But the other counties in Ireland, in the Republic of Ireland, had relatively low numbers, and some of them actually had zeros in there. As I say, because this is quite an early time. And that's the density in terms of 100,000 population that we're seeing there for the cases. So as I say, we're going to start with a simple model that basically says that the number of cases seen in each county is basically Ni for county I, and it's a zero inflated Poisson model with lambda I being the rate for county I, and in this case a global theta, which means that the non-reporting probability was about the same everywhere. And lambda there you can model as the rate R plus the log of the population. Log of lambda equals that, so that we're basically controlling for the different populations of each of the counties there, and we're trying to estimate the rate. So in this case, we're actually saying the rate is also the same everywhere, and the count is just proportional to the population, but the constant of proportionality is the same everywhere. So we've got these various things there. We've got the theta, which is, as I said before, the mean of the underlying population, then the rate of infection, which we assume to be the same everywhere, and then we just allow for the population. And that's a sort of simple model to predict Poisson regression, for regression of the rates. Now, we can actually calibrate that model, given the data we've got, using a tool called STAN. And STAN is actually a programming language for Bayesian inference. And what happens with STAN is, although it's actually a different programming language, you can sort of use it inside of R. And it's a language that's only really designed to do one specific job, which is simulate things from a specified probability distribution. And in this case, given it's a Bayesian approach, what we're interested in is the posterior probability distribution of the parameters we're interested in. And what happens is you basically write down the likelihood for those parameters in STAN. You write some code to produce that. And when you run STAN, it draws things from that distribution. Then you can look at it to draw inferences. So rather than actually theoretically working out a posterior distribution, it just generates lots and lots of numbers from that given probability distribution. And so if I do this in STAN here, it just gives me this code here. So that's my STAN program. It looks a bit like, I suppose a bit like C, but it's or C++. But what you have to do, without going into a lot of detail, you first define all the variables that you're going to use in it. So for example, the log population you can see in there, N, which is the number of counties we've got there, and a few other things. Then we have the parameters. Now, the things that are the data are just fixed quantities that are supplied to the R program, to the STAN program from R. They won't change. The parameters are the things in there that you actually are interested in estimating, and that's the thing it draws the probability distribution, the simulated values from. So those parameters there, the ones I'm wanting is log lambda and theta. The other thing it allows you to do is you can put the upper and lower limits on what you'd expect theta to be. So we know that theta is a probability, so it's got to be between 0 and 1. And you can see basically that means that it won't randomly generate anything outside of those areas. We also have what are called transform parameters. So the rate in there is something that I can generate from the log of lambda. So that's not the population, that's actually just the rate when you've allowed for that. The rate is e to the log of lambda times, in this case, a million. So this is basically a rate in terms of cases per million. So that's not a thing that you're generating directly from the model. It's a transformed value of that, because we might also be interested in the posterior distribution of what the rate is of the infection. And then the final bit is, again, without too much complication, this is actually specifying the model, and this is actually specifying the likelihood of the model. The key thing there is a probability distribution function for log Poisson mass function, which is basically the zero inflated Poisson, which is zip log LPMF, and then given x, and then theta and the mean. So that gives you the data, the transform, the parameters and transform parameters, what the model is, and that's actually just a string in R. What you then do is you set a variable in R to be stand model of that code, and then you can do things like run it and pull the results out and so forth, which is what I do sort of later on in the model. So I'll put the code away now, just having shown it. And those are the posterior distributions of the rate and of the theta, the probability of non-reporting. So what it's doing there is probably saying that the, in terms of those are the mean values shown on those red lines there. The rate looks at about 28 per million, something like that as a peak, and you can see the spread of it as well on that. And the outcome of the theta estimate, well, the average is about 0.17, 0.18. If you're interested in the modal value of it, it's a little bit lower. But again, that's sort of saying that it's in this non-reporting thing here, it's saying that the non-reporting rate in average is something like about 18%, or at least it was at that point in time. And there we go, I've actually put the values in there, and it gives you the, sorry, I read the value wrong, it's more like about 0.12, about 12% for theta. And again, you can work out the upper and lower credibility intervals, which are essentially like the Bayesian equivalent of confidence intervals. You can see the intervals there and what the actual estimated values were. We can do the same for the negative binomial distribution, and that has, you can work out the rate from that, and it's giving you sort of slightly lower overall rates. The difference between the negative binomial and the Poisson is that the number of counts that get reported assume there's some degree of clustering, so that the cases aren't independent. So, for example, if there's someone infected in a household, then the chances are maybe more people in that household are going to be infected, and it's not independent, so it's more prone to clustering, which sort of means that the average might be a bit lower, but sometimes you'll see higher cases because of people, these clusters occurring. And the theta, though, is a very similar sort of concept, which is the non-reporting rate. But again, theta could arguably be smaller with this because you're allowed more possibilities for the variability in the count because of it not just being purely Poisson, because of the degree of clustering. So you can sometimes get more houses getting zero and other houses getting a lot of cases, and the average sort of being a bit different from that. And then the likely sort of outcome you get for the non-reporting rate will be a bit different. In this case, it's a little bit lower. And I won't go through that, but that's the code for this. And again, it's very similar, just it has a different model part, really, and more parameters in there because it's got this phi parameter, which is the sort of clustering parameter. But you can use the same approach using Stan, and those are the estimates you get. We can write those down. The rate's very similar again. It's the theta that differs more. And if I look at this parameter phi, which is the clustering one, it's harder to interpret directly, but that's the range for it. Okay, so I've got two models now, and what I'm interested in is whether my zero-inflated Poisson or my zero-inflated negative binomial is actually a better model of that data. What we do to think about this, before we get to the model averaging, there's going to be a slight diversion here, because rather than thinking about the probability of the model given the data, we're going to think about the probability of the, and that's sort of for model I, the data given model I. Now, the probability of the data is something that you don't often see in a lot of analysis. So it's not the probability of your parameters given your data. It's just literally, you've got a data set with a number of quantities in it. What's the probability given a particular model that you'd have got that data? Or it could be a probability density if it's continuous. And by that, I don't mean just the model with a specific set of parameters. I mean also given the possible spread of potential parameters. Now, in a Bayesian analysis, that would effectively be the prior distribution for the given parameters. So what you're basically saying is, okay, I've got a certain data set. What's the probability I've got that data set when you count that up against all of the possible data sets I could have got given my potential parameters and the probabilities of any given data set given the model. And we can then, if we work that out, we can sort of use Bayes' theorem to change the subject of that and turn it into the probability that the model is the correct one given the data. So basically, the way we tend to work this is we work this thing out first and then we try to get to that, and then when we've got that we can do the model averaging. But the actual probability of the data given the model is quite a useful thing to think about in its own right. Now, to do that, using Bayes' theorem, what you also have to have is these prior probabilities that each of the models is the true one. Now, usually the most sensible thing to do is if there's m models, there's just 1 over m, so they're all equally likely to occur. And if you do that, then basically, if you've got the probability of your given data set, given each of the models, then effectively it's, for a particular model K, then it's just the probability of the data given that model over the sum of the probability of the data given all of the models, including itself. So that gets you back to the number you're most interested in. But the probability of the data given a model is of itself interesting because it works a bit like something like an AIC in that when you have an AIC, okay, there's two things really that you're thinking about. One of them is how well your model fits the data. So, models, if you're doing, say, things like regressions, ones with a high residual sum of squares look less likely than one with a lower residual sum of squares. But you're offsetting that against model complexity. The problem is if you've got a model that's very flexible, then it's quite easy to get a low sum of squares. And are you overfitting? And this is sort of what this probability of the data given the model thing actually does, as explained by this diagram here, because essentially what you're sort of saying is, well, if I've got a model that doesn't fit the data very well, so my data might say be non-linear in shape, then the best model I could ever get with a linear model would be something like that. So you're never going to get, given that model, the probability of getting data like you've got is actually quite low. Because if you're using a model like this, then all the data sets that it generates are generally things with data hanging around this line, and the real data isn't really anything like that. So what tends to happen then is the probability of your data is never going to be that high given the model you've got. If, on the other hand, you over-parameterize, then you could certainly get data like data like the stuff you've actually observed, given the model. But let's say you've got data that was roughly, if you're fitting a curve, a quadratic model. Suppose that I'd also put in a cubic model, then certainly it's quite probable I could get data like my quadratic in my cubic model. But I could also get loads of data sets, potentially, that were nothing like that, because they've got a cubic part to them as well. So basically, if you look at the data set you've got, then yes, that's quite, it's reasonably likely you get it in that model. But you could also get all kinds of data sets that didn't really look anything like your data set with similarly high probability. And because you're normalizing to make it the probability you're interested in basically is the probability over all possible data sets that could be generated, and make that one, because you've got all these other data sets that are quite likely that don't look like your one, when you do that normalizing, it makes the probability of the data given the model actually drop. So basically, you get a low thing when you've under-parameterized, but you also get a low thing when you've over-parameterized. And that's what this graph's about here. So it's a bit vague. I've used the term feature richness here for what's in the data. And an over-parameterized model then says, well, if that's the amount sort of feature richness you've got in your actual data is sort of here, then the under-parameterized model doesn't do very well because it's already said you're not very likely to get data with that kind of feature richness. The over-parameterized model, however, because it's saying you could equally likely get data with quite a lot more feature richness than that one, that actually, because the whole thing's got to be an area of sort of 1 under here, basically gives you a lower value for the observed data. And then the best one is the one that's sort of plausible, that kind of does generate data of that kind of feature richness, but not data that's sort of a lot more rich in features. So basically, you can use this probability of the data given the model, as well as a way of getting the opposite way round of the model given the data. You can also use it as a way of actually choosing which models are most plausible. So in fact, you can use it a bit like an AIC as a way of picking out the direct, the best one. But the point is, because it also gives you a tool for comparing models and looking at mixtures, as well as telling you the best one, it also can tell you how to model average, and particularly if that's useful if, as I say, the best performing model is quite close to some of the other models, and then it'll give you a way to work out those averages. Now, the only other complication is that it's rarely possible to work that out analytically, because if you've got, say, a data set with millions of observations, effectively you've got, let's say you've got 1 million house prices. You've basically got a 1 million dimensional distribution of data to look at. So it's usually very hard to actually deal with that analytically and come up with the estimate of that probability of the data given the model for a number of different models. And as in a lot of cases when things are difficult to do analytically, you basically get 2 choices. You can either simulate from the model that you're wanting to use, or you can approximate it, and so you get an approximate answer, but you can usually get that a lot quicker. So in other words, you can get a sort of an accurate answer, but it won't be quick, or a quick answer, but it won't be as accurate. It might, if it's a good approximation, it will still be useful, but obviously you'll get a more accurate result if you use the approximation. And one of the things you can do is, which is an approximation, is the Bayesian information criteria, which is this quantity here. So K is the number of parameters in your model, log of the number of cases minus 2 log of the estimated likelihood of the best fitted one. And to derive that is, well, I've got really time now, but that is this quantity, the BIC, which works a bit like an AIC. And you've also then, if you've got the BIC for a given data set and model, you can say that the probability of the data given model I is approximately equal to e to the minus the BIC over 2. So that's an approximate way of getting the data, probability of the data given the model. A more accurate, but much more computer intensive approach is something called bridge sampling, which actually, given that Stan works by sampling from the distributions of the posterior distributions of the parameters you're interested in, you can base an estimate of it using this idea of bridge sampling, which is relatively complicated but can be done. And there's a function in R called bridge sampler from the bridge sampling package. When you run a Stan program, you can get an estimate of this log of the probability of the data given the model. Now for this example here, since I've used Stan for the other stuff, I'm going to use the Stan approach. And so when I compare the Poisson to the negative binomial models here, I've got my estimates for the 2 different logs of the probability of the data given the model. For Poisson, it's sort of minus 62 point something. For negative binomial, it's minus 53 point something, then you can look at the differences of those, because when you're really interested in the ratio between them, then when you take the exponential of those differences, you get the relative odds. So actually what it's saying is that the probability, or the odds of it being a negative binomial model are about 4,400 times the odds of it being the Poisson model. And if you turn that into the probabilities of the models, in this case, the probability of being negative binomial is about 0.999 to sort of 0.002. Well, anyway, it's, they're much more likely. So in this case, probably you can just use directly the BIC or the bridge sampling coefficient, and you can see there that it's far more likely that the negative binomial model is correct in that circumstance. So it wouldn't even, you could do model averaging here, but it would probably be less helpful because evidence is so strongly in favour of one thing over the other. But we could now come up with some more models. So we look at the both binomial and Poisson for each model, and then I've got 3 possibilities for the rates in each of the counties for the models here. One is that they're constant, which is the model I've been using. 2 is that they're different, but there's no spatial process going on. So the probability for one county distribution for the lambda rate is different, is independent from any of the other counties. And the third model is an intrinsic conditional autoregressive model, which is basically a model in which there's a correlation between adjacent counties. So we've got one sort of spatially smooth model for the varying, one that each county just varies independently, and one where they're all the same. And we do that for Poisson and binomial. When we run the results of that, we get ultimately those are the probabilities of each of the different models. And you can see there's more of a sort of set of possibilities. So in fact, Poisson, but with random values for counties, actually has quite a high probability of about 0.42. But then there's reasonably sized all of the negative binomial possibilities, which add up to more than, well, they add up to about 0.58 or so, just under. You can see there what the probabilities are for those. You can also see that the other 2 Poisson probabilities are virtually 0. So we've got 4 different, pretty much non-negligible probabilities of those models being true, working through to the model given the data. And then if we look at the actual estimates of theta for those 4, we've got things like the negative binomial ones tend to be a bit lower at about 10%, and the highest one is the Poisson, which is about 11%. So they're all actually remarkably similar, which is perhaps why there's not strong evidence that one model's better than the other, because they're all giving you similar sort of levels for the rates. And what we then do is we say, well, okay, those are the posterior distributions for the non-reporting probability from all 6 of those models. The numbers at the top there are the relative probabilities of them. And I can then take my weighted posterior distribution, and that gives me my estimate of the probability of non-reporting when I'm not sure which of those models to use. Although post-data analysis, I've got better idea in some cases than in others which are the appropriate ones. And that's doing the same thing actually with the maps. So again, you can see some of those maps are fixed because I've assumed that the rates are the same everywhere. Then the last column there is for the more spatially smooth estimates. And the average model, it gives me the bigger one on the other side, which sort of again gives you an estimate of the rates of occurrence of the models there, but allowing for non-reporting. So it's actually, sort of getting you a true rate there. And this sort of thing can be quite important because although, this is what happened in COVID, it is important to know how many cases, or at least estimate how many cases are really out there. Okay, a new, virus might come along. We won't know exactly. People, the same situation may well happen, people won't know the symptoms of it. They won't know, the best and most effective way of testing it and things like that until we know a bit about it. So it's more just a bit of giving us an idea of what's going on and ways of trying to estimate, some of the things like non-reporting, given what we've learned from this. So we're nearly done with this now, but I'll just give you another very quick example. This is about the UK Brexit referendum, and the diagram there gives you some idea of kind of what I think of the idea of Brexit. But that's basically a thing I want to analyse. I'll go through this one quite quickly, but the point is that in the 2016 UK referendum on leaving the EU, the outcome was actually 51.9% majority, so it was a very, very close thing really anyway. And the map there suggests that the overall figure, which is showing for each of the parliamentary constituencies what the vote values were, basically suggests that the overall figures were quite varied geographically, and in particular you can see Scotland was actually quite pro-Remain, as was London and some of the surrounding areas, and a few other areas dotted around the country as well. But the point is, we can see therefore they're different, but if we try to predict the votes using some various census data, what we're interested in again is another geographically weighted regression type problem, like do the drivers of this actually change over space. And so I've got there four, one is the independent, is a dependent variable, leave, and then four other variables that are thought by some commentators to have affected the outcome of the vote. So it's older, people who are actually born in the UK, the turnout of the 2015 general election, that's a sort of measure of engagement, the number of people that actually voted in one of the election the year before, and the percentage of the electorate stating their religion as Christian. Again, it's a bit about identity and sort of the UK identity. And each of those variables could either influence leave in a spatially heterogeneous way. So in other words, that value would have more influence on leave in some places than in others. So you'd want some kind of spatially varying coefficient. Influence leave in a homogeneous way, so just the same coefficient everywhere, or not influence it, so it's just zero, and that thing doesn't affect it. The other possibilities, I've looked also at when I do the analysis in terms of the spatially varying thing, what space do I do things in? So I've used this sort of cartogram space for each of the constituencies in the maps. These are actually the physical centres of the constituencies. When I'm actually fitting things like a spline curve, which I'm doing here, the location of x and y matters. So what I'm not also sure about is which of the two spaces to use, the physical or the cartogram. So again, I put those in. So the way I do it, I use, as I say, thin plate splines as a way of measuring, of modelling things that change over space. You could use lots of other things, Gaussian processes, things called soap film splines. And what they're quite nice at, what they do is they sort of model what would happen if you had a sort of soap film under tension in a particular rigid framework. And that's sometimes quite useful because if you've got something like England and Wales and Scotland here, if you just use Euclidean distances, it might be that sometimes you get influences, for example, between Wales and North Devon, which might not actually make sense. If you use the soap film approach, it basically models things as though this was sort of a metal frame, and you're looking at soap films in between there, and what happens if you use those is that you don't get any effects, when there isn't a solid land link between the two places. Now, I've not done that this time, but the point is, again, there another possible way you could look at the data. And that, if you use the GAM package in R, you'd express models with things like this. So that one, for example, has got the born in the UK as a varying coefficient, the turnout as a fixed one, and the other one's a zero. So there's a lot of models you could do there. In fact, the intercept I haven't put as a zero, but you've got fixed and varying. There's two possibilities there. Then there's three each for the four coefficients. And when you multiply those all up, you've got 162 models. Then, as I say, you've got this cartogram versus physical space, and that doubles that, so we've got 324 models here. We need to compute those things. Now, that's going to be very intensive while I've gone through doing it all through Stan. So I've just done it here using, well, that's just explaining how you do the Bayes theorem thing, which I've already explained. But what we then do, sorry, have I got that? Yes. Basically, sorry, I just realised the one thing I haven't got in there is the result. Apologies for that. But what basically I did then was I used the Bayesian information criteria to do that. When I did that, what we got ultimately, although I can't find it on the stick there, is we get estimations, and I think it worked out that the best approach was to use the cartogram space for 3 of models, of which there were 4 that were significantly different from 0. And I think they all had the turnout in as a spatially varying, and some of them had the election engagement being fixed, some had them being varying, and then we got each of those had roughly similar probabilities between them of something close to a quarter each, and then the rest of them were very close to 0. So it did tell you that some of the models were pretty implausible, but it also told you that, again, it wasn't one clear winner, there was about 3 or 4 possibilities, and then you can go on to use and draw maps of the estimated values, which, so that this is fallen off the presentation there. But the idea and the methodology is there, and I think those were the right outcomes. And what I'll do is I'll put I'll find the rest of those slides and put them up for you later. So I'll stop that there. I think we've probably used enough time there. So well, thank you for listening. I'll stop there.
I'll go well.
Yeah.
In terms of computation of power, for example, how many, let's say, data points the number of rows for analyzing all of this spatial data for UK was there?
In the data, for that there are, it was about, it's just over 500, because it's a number of constituencies, yeah.
And it was all on in Stan, right?
No, for that I did it just using R and using the GAM, because you can reasonably do Stan approaches that will calibrate a model like that, but the problem is I needed to have done 324 of them. Mm-hmm. And that's where it gets to be quite, well, just on my laptop, doable, but not doable very quickly. If you're going to use some cloud-based tools, you probably could do it then, because it's basically what you call an embarrassingly parallel problem, because if you just split up the model, well, the 324 models, each one will be an individual run of Stan. So if you actually had 324 parallel processors, you could just totally run it in parallel without having to do any modifications. So you could do it that way, but I didn't have the access to that at the moment. Hi, yeah.
But you are saying that it's 500 observations like for one geographical region, I guess?
No, that's for the whole of the UK. So it's the vote outcome for each constituency in the UK for the Brexit referendum.
From various regions. And
yes.
You said that having 500 individual observations makes it on ordinary laptop, according to your method, quite tedious computation. You did it in cloud, but meaning on ordinary computer it would take, I don't know, weeks, months?
No, sorry, no. What I meant was, I did the, each individual model has 500 or so individual observations.
How many models you consider?
324, so you've got to multiply them.
So for this kind of computations on ordinary laptop without parallel computations, how much time?
I would guess it probably wouldn't be that, maybe about 8 or 9 hours.
8, 9 hours.
So it's doable, it's just I get excited and I want to see the result quicker than that. But yes.
Here's the second part of my question. It was all on in R, but wouldn't it be much faster to, for example, in C++ or Rust?
Well, that's where Stan is useful, because although Stan, looks a bit like C++, there is actually the way it works is it converts the Stan into C++ and then compiles it and runs that. So the when you actually, if you tell Stan you want to run, sort of say 10,000 simulations, that's all done in Stan. So it's still slower a bit than just doing a straightforward regression, because you are still generating lots of numbers from a random process. But no, Stan is using C++. So effectively, as I say, the way it works, when you when I showed you the bit where it showed you the Stan model, and I put it into a character variable, and then just said Stan model with that program, that's effectively compiling it into C++ and linking it into R.
Okay, thank you.
So yeah. But as I say, you can, the various tricks you can do, like parallelizing and things like that. And it would, I think, my estimate maybe 8 or 9 hours might not be perfectly exact, but I think it would be in the right order of magnitude.
Hello.
Hi.
I'm not expert in this area, but I'm here to improve my general culture about this topic. And in practical terms, I understand the science of all this. It's very interesting topic. In practical terms, how we improve this methodology? The first example about the taxi example, how do you improve the action to make decision on the taxi?
Well, what it would do, I guess, is it would give you more of, if you've got the waiting time, and if you have knowledge of which of the possible models and the distribution of the times, what you get is essentially a more accurate estimate of the overall distribution. So, for example, if you wanted to know, what's, say, the 90% tail of how long you'd have to wait to get an idea of that, so that, in the worst cases, that's how long you'd have to wait. Then you might decide, in that case, is it worth trying to phone another taxi or something like that, because, it might still be that the 90% end of the delay might be tight, but you might still get the train. And also, it might be useful if, say, two things were equally likely or have very similar probabilities, but were actually quite different kinds of scenarios. And you could combine those in such a way that rather than just assuming it was one of them, and maybe one of them had a very long tail and the other one didn't, you get a more. So that's sort of how I would do, if I was trying to deal with that and turn that actually into a sort of policy decision as to whether to run, get another taxi, jump on a bus or whatever.
Thank you.
Okay.
I have a question as well. I'm thinking about these COVID cases. Because of different regulations that were imposed, the pattern of cases was also changing, right? So we had those waves and then the times where it got somehow silenced. How is your model kind of addressing this situation in real life? Is it like having different models? I assume that for some models they would be better for these spikes, for some they would be better on these flat periods, and then what you are doing is basically changing the weights in the weighting?
Yes, you certainly can do that. So what you're effectively doing is, if you wanted to model that, what you do is rather than, say if I was attaching a probability to each model, I could further model that by the, let's say you've got n numbers that have to add up to 1 for each of the models. You could actually make those as a sort of a vector, as a time series, so that as time went on, there was a chance that, something might become more accurate some of the time. So yes, if you didn't do that, it would just kind of weight down the spikes. But if, on the other hand, it looked as though it's more appropriate now that you switch from one model to another. You can do that as well. So you have an underlying way of assessing which of the model is working best at the moment. And you could, one very simple way you can do it is just actually to recalibrate every so often, and maybe have some sort of this is perhaps less statistical theory, but more a practical use is, if you notice your predictions weren't very reliable, then just trigger a recalibration. So yeah, you can, which I guess for the COVID that would be important.
Okay, something else? No? Okay, so thank you very much
Thanks.
for the talk. I have just a token of gratitude from the faculty.
Oh,
so
thank you.
There you go.
Lovely.
Thank you all for coming. The seminar will be also posted on our faculty YouTube channel, so you can also send later on things